behind where I'm running a white video, 10-hour video on YouTube on both monitors. So I have this nice forward light there. It works great.
All right, so
you got to improvise the lighting kit when you don't have a good one.
Oh, I know. And actually, that reminds me, Trenton sent me a set of lights that are really, really cool.
I wish I could actually control the brightness on this camera, but there's not really any controls in here to do that. That's the problem with these free streaming apps. They don't have a lot of
controls for that.
Yeah.
All right. We are live now. And I am making it public if my slow computer ever works. All right. So on my Facebook profile, there is the link to it that we can all share around now, I think. Awesome. So we are live, apparently.
Is there a way you can see how many people are viewing?
Yeah, on the live stream on Facebook.
Did you tag me?
There we go. All right, so things are going slow. Sean Mandel has joined. What's up? So I'm going to be getting chat on this side, but I don't know if you guys will be able to see it. All right. What's up, Will Nelson? How you doing? Friend from Toronto. What's good, fellas? Hey, Sean. All right. So I am live now. It is a public. We are going to share it, and I just wanted to start out this stream by saying, what's up, guys? Drone On and On has had its name changed to Optimized Drone out of respect for a fellow pilot. So, what's up? How's it going? Welcome to Optimized Drone. Matt and I are sitting here with Ryan Harrell. Harrell, sorry, my bad. Ryan Harrell, who is, in my mind, a guru of tuning, but he doesn't seem to think so.
Well, I mean, is it something you could ever really guru?
No,
I mean...
never, ever. It's something that, like, even though I've delved deep, I've found pretty much every JC or Project Blue Falcon video. I've found every Bardwell video. I've watched a lot of your videos, a lot of other people's videos. And even then, you still come back going, wait, what do I need to do? Like, what am I setting up here? And with all the new stuff coming along, like Betaflight 4.2 and all the filtering and the BL Heli ESCs not being able to work with that filtering and all that, it's just got super confusing. Ryan,
there's a lot of variables.
Yeah, Ryan has actually gotten me hooked on JESC, guys. It's awesome. I love it. Most of my rigs were BL Heli S, and they fly great on JESC. The only problem is it costs a little bit of money.
Well, I mean, you're paying for that on BL Heli 32. It's just integrated into the price of the ESC. So
yeah, I
mean, it's really not in the end any more expensive. I think it's just a different way of approaching it.
Now, which do you actually recommend? Because if we're talking about BL Heli 32 versus the either Jazz Maverick or JESC sort of protocols, which would you prefer?
Well, I mean, obviously, BL Heli 32 with the 32-bit processor is going to be the best way to go because there's additional hardware layers in the STM processors that they use in those. Not all of them are STM; some of them are other brands. But there's additional layers in the 32-bit chip that can handle that, DMA and things like that aren't present in the BL Heli S ESCs. It takes a lot more time for the BL Heli S ESC to process that during the commutation cycles, and it's a lot more overhead. So, I mean, Thorsten, Joe Lucid has done a fantastic job of getting it to work in the 8-bit the EFM series EFM8 series processors that are on those BL Heli SCSCs, and that's fantastic. But obviously, I think you're running a better solution in the 32-bit processor. That being said, there are so many economy BL Heli SCSCs out there that are just a steal for the price. And I have, I have like 20 CRODs running over there, and half of them are on BLHES, and I can get the BLHES ESCs for super cheap. So, like, if I'm throwing a rig together that I don't really care about too much, just something to bash around.
Yeah.
Why not, right? And it lets you have all of those features that you get with the 32-bit without having to spend the money on it. So, if you're buying new ESCs and you want to have, something that's going to be a little more future-proof and that's kind of, modern technology, then the BLHE32 is definitely the way to go. But, if you're saving a few bucks on ESCs, you can get some really high-quality BLHES ESCs for, $2-3 in ESC less than what you're getting for the 32s.
Hey, Dan, refresh that clip. I spelled it wrong the first time.
Okay.
Mooly Rotors.
Ooh, I didn't know you changed your name, too. Mooly Rotors.
I like it. Oh, man, the one that always gets me, like, half the time
I don't want to
I
be called a
type
racist or something like that. So, come on.
when I type it, half the time it comes out Mookie Rotors. Like, I mean, David Avery Mookie, I'm sure that's perfect for him.
Yeah, for me, it's my phone likes changing FPV and TPU when I'm talking about 3D printing. Mm-hmm. It always changes TPU to just U, and like YOU, and it changes FPV for some reason to capital F, lowercase AP, and then capital V. And I'm like, when did it even learn this? Like...
You must have tapped it once when you were making a mistake, and it's like, oh, that's what you want forever and more.
Yeah, exactly. So, Gank, Mooly Rotors is... the website is actually online, guys. We're trying to get people on there. I have the pleasure and privilege of being the very first order on his new website, which kind of pissed him off.
Well, it was little, It was, hey, look at this. Oh, look, I ordered. Wait, no.
Yeah. He sent me a tester link to be like, yo, tell me if my website works. And so I went straight into the order, bought a frame, clicked PayPal, ordered it and everything. And then I just get this message, wait, what the? Hey, oh, man.
Dude, come on.
That's fantastic.
So... But for all that don't know, Ryan's website is miniquadtestbench.com. And I have been exploring it. I explored it a little bit previous, but the past few days, I've really been diving into it just because I've been talking to Ryan. And it's awesome. If you guys have any questions about thrust ratios or how the motors will work, if they're noisy, if they're not noisy, look up your motor. Look up what motor you've got on his page. You can match it with whatever props you might be thinking of, and it'll give you the thrust to weight ratio. It'll give you a full-on graph and all the data you might possibly need. And this is what Ryan does. So you have what is it? It's an Arduino-based tester unit, right?
But it's actually The one that I'm using right now is based on the T2C protocol, T2C chip. It's based off the TI Launchpad T2C board that you can get for like $14. Nice. My whole goal in this thing was to make it as replicable and easy to reproduce as possible. Like, I wanted an inexpensive, reproducible test environment that could, very easily be duplicated. I mean, the whole point is to make peer reviewable, peer supportable, data accessible. So, I mean, we've really I have another guy, Brian Bailey, out in California or Oregon, who's doing some testing for me on the low KV side as well. So we've been we spent originally with Ryan Evans actually set that up. He helped set that up originally. We did a bunch of cross-site testing to make sure that the environment variables were fixed and all of that stuff. So. But in the end, honestly, what we've been doing recently, we haven't really been publishing results to the, writing articles and stuff because, I mean, there's only so many times you can write the same things over and over again about these motors. So basically, we've been pushing it straight to the Data Explorer. So if you haven't seen any new postings on the website, skip over to the Data Explorer and look through there because there's a lot of new stuff that's just getting populated into the Data Explorer. And we're not really bothering as much with writing articles. Neither of us are huge fans of writing them, and we just would rather just put the data, because the data is what people, it's what it actually is.
And I find the graphs are very, very easy to follow. You're like, okay, I got this motor against this motor. There they are. Oh, perfect. Okay. Yeah. Like, it's so much easier than just reading a big, long scientific article about.
Well, right. And I mean, most of our articles were really just talking about, what's the build quality like? How's the tolerances on this? But honestly, the manufacturing of all of these motors these days is so good that, like, even the low-end motors, like, the difference is really in the materials, not in the manufacturing quality. The machining is great. Everything is good. The only difference is that they're using a softer metal, or they're using, lower end magnets, which that shows up in the test results anyway. So, but actually what I've been working on right now is my test stand is actually torn apart at the moment because I am reprogramming a lot of the software to add some features to that. So I'm adding D-Shot protocol to it and some other things like that. My goal is to do some testing on 24 versus 48 kilohertz and what we can actually see in that regard, as well as doing some testing on like width versus height. I have some motors here from Bob Ruby that he sent me to check out they're these like super wide, super short motors. Right?
Yeah,
like a 2004 or something.
Yeah, I have one of those, and these are crazy.
They're what, 3-inch motors, or are they the 5-inch toothpick ones that he was?
Yeah, I have a couple of variations here that I'm going to be looking at, but the goal is to compare it against the stator volume that's basically the same stator volume, but looking at the height instead of width, and comparing like if I go really short and really wide. And I've been talking with Bob a lot about this as he's been flying them, and we've been exploring it. So there's some really interesting things there that happen when you go that wide and with that short, because they're only like 3 millimeters tall, but you're talking about significant width. So they seem to be fine up to about 20 millimeters ish. Then as soon as you start getting up into like what would be normally considered 5-inch motors, it seems like there needs to be a certain amount of height in order to maintain enough torque to actually not desync properly, when you run in heavier props like that. So he's still playing with some stuff on that, and still planning on doing some more testing on it if I can get my stand put back together. But it's always fun trying to shoehorn in the D-Shot protocol. The T2C microcontroller is a little bit finicky when it comes to some of that, but all the source code is up on my website if anybody wants to take a look at it. So
I have a whole giant box of like Pi modules, Arduino modules, all that stuff. I was actually thinking of building some sort of a test bench for that. So I might hit you up. But those short and wide motors, you and I actually talked about those a few weeks ago. But it wasn't the Bob Ruge ones. It was the fact that I was building that 11-inch that had the really short 750 kVs.
Right.
They're like 5010s, so they're super wide, but they're really short, and I love them. I just love them. Like I've tried the bigger motors that are the super tall stator motors, and these ones just have so much more torque and are just so smooth in terms of... Yeah.
Well, actually, I think what it is, it's more smoothness than torque. It really... Yeah. There's a lot of factors involved, but there's... And this is what I'm hoping to find out here with some of this more additional testing, but from what I have seen so far, it basically, to me, seems like mostly a myth that the wider you go, the more torque you get just from the width.
Yeah.
In the end, what I have found in my testing is that overall stator volume has more to do with the torque production than the width versus height. As you go wider, you have this competing thing between the momentum, the moment of inertia of the bell, because the further out you go, you're more moving that mass away from the center of rotation. It has a larger moment of inertia, which means that it has to work harder to accelerate. But it also has a longer lever arm. But it's this balance between the mass moving away and the lever arm that's being produced. There's a lot of factors that go into that, but in the end, you're producing more magnetic torque from a taller stator. It's the overall stator volume that's producing the overall magnetic torque. The torque of the inductor that's the coil there that's pushing that magnetic field against the bell. So. I think what happens with width is that it makes things smoother. and I've been talking with Bob about this a lot, but as you're going out, the other thing that's happening, if your number of poles are staying the same, you end up with a higher velocity as the magnets pass each pole.
Yeah.
And if you're not increasing the number of poles, then that means that velocity, the linear velocity as it passes the stators, gets faster and faster as you go outward, which does all kinds of interesting things to the BEMF signal, the back EMF that's being detected by the ESC. And that's part of why I think that there's desync issues with some of these really wide stators. Now, obviously, you start going wide enough, you start adding poles, and that eliminates some of that. But there's still this relationship between the number of poles, the linear distance that the magnets are having to move, and the speed of the bell at a given kV. And I think that's why you tend to see those pancake motors, like the ones you're using there, tend to be low kV, like 700, 400 kV. The really low kV motors are the ones that are the really wide, short ones. And if you want to get higher kV, you really have to up the stator height in order to sufficiently deliver enough torque on that velocity as the size goes up.
Yeah, I totally hear that. And,
isn't the relationship more like you were saying, pole size, right? How many poles we have in the actual area of the pole versus the whole area of the whole stator, right? So if you had less poles but larger pole surface per pole, then you're gonna have more torque, but not necessarily more power. Is that what you're saying?
Well, I mean, it depends on a lot of factors. A lot of that has to do with the windings, the way that, the amount of copper that's around the coil, things like that, because that all changes as you change the physical size of the stator volume as well. So it's all a relationship between how the magnetic fields flow through the stator, how much material there is, how many coils there are around it, and all of that stuff. I mean, there's inductive formulas that you can put all of that through to see how much inductance a given coil is generating, how much magnetic flow it's actually generating, things like that. So, but yeah, I think the other problem that we have is that most of the motors we're dealing with are such small scale. So differences like that don't necessarily always behave in the way they do at scale. So, you start going larger motors and things start behaving differently. We can do different things on larger motors that we can't necessarily get away with on smaller motors. Like the Tesla motors use very interesting, angled, like V-shaped magnets that do really odd things. They use Hallback arrays and all of this stuff that work great at scale, but you can't scale down to our size. They just don't work at our size. So lots of interesting stuff.
Brent, it's the kV is not. It's actually a calculation of the amount of RPMs per volt that each motor has. So the more volts that you have, the less kV you need to reach a given RPM.
Yeah.
So
it's actually
for 4S you need more kV to reach the certain prop speed. It makes the higher voltage makes it a little more efficient, less current per revolution.
See, there's actually a couple of things here that are really interesting. So the kV is actually an electrical constant that is actually the amount of voltage that's generated by a specific RPM. So it's actually the inverse of what most people think. So if you were to spin the motor at a constant RPMs through an external source and then hook a multimeter up to the leads, the kV is actually how much voltage you're going to get at a particular RPMs being pushed back out of the motor, not being pushed in. So the forward relationship between a voltage and RPMs is a byproduct of that. But the real actual value is the inverse. So what happens is that often the measured kV through the external drive method, when you run that through, you run it through a variable. It has to do with resistance of the windings plus the voltage at the there's a formula that you have to plug it through that gives you the actual electrical kV of the motor. But the forward kV of the motor, the no load RPMs that we usually equate to kV, doesn't necessarily always line up to the electrical kV. There could be some difference there because of bell mass and things like that, and even things in the ESC as far as how the commutations work in the ESC, and how they drive that forward thing. So that's the kV is we use that number as kind of a catch-all to say no load RPMs, but no load RPMs and kV are not necessarily the same thing. It's kind of I don't know that really matters in the end, but there are things that change when you think about that relationship, not necessarily being what we always traditionally think of it. The other thing is that depending on what you're doing, almost always you're actually losing efficiency when you go up in voltage, not gaining it. This is probably the biggest myth in this hobby. Like everybody always says, oh, you go up in voltage, you're gaining efficiency. And that is not true. Like you're assuming that KV stays constant, you're going to lose efficiency by going up in voltage. Now, if you drop KV back down, there is a relationship between the velocity constant and what we call the torque constant, which has to do with how much current it costs to create torque. So what you end up gaining is you gain some gains in terms of the cost of torque production by going down in KV that offset the losses from going up in voltage. So you end up in about the same place by dropping KV to the equivalent thing, but you actually usually end up with maybe a 2-3% loss in efficiency by going to an equivalent voltage, equivalent KV voltage combination too. So like by going down in voltage, you're going to gain efficiency by going down in voltage.
That was always the argument with me, because you're adding cells to a battery. You may be dropping the milliamp hours a little bit, but your battery's roughly the same weight as a 4S versus a 6S. I mean, I'm still on 4S for racing, but I mean, that's just personal because parts haven't broken yet. So
there's a lot of factors that go into that, because efficiency is measured in watts, not current, right? So even if you're dropping in current because of Ohm's, well, it's not even Ohm's law. It's a byproduct of Ohm's law, because Ohm's law is equals IR.
It's going up.
But but to a certain extent, again, if KV stays the same, if you're not adjusting KV, you're losing significant efficiency. Like it can be up to 25% efficiency loss just by keeping the same motors and going up to a 6S over a 4S. So again, some of that depends on where in the throttle you are, though, because competing with the electrical efficiency of the ESCs and the motors that you're losing going up to 6S, you're gaining an efficiency in the batteries themselves from the electrochemical reaction. So there's some electrochemical things going on in there that make the batteries more efficient at generating large amounts of current as you go up in cell count. So if you're hammering that battery to the wall, the entire pack,
like racers,
you're probably going to see an increase in efficiency by going to 6S over 4S, because voltage sag is not allowing you to actually deliver the full capacity of 4S battery. So you end up pulling less milliamp hours out of the pack at 4S than you can out of the pack at 6S. And even on top of that, there are other things electrochemically that are happening that actually make the 6S pack more effective at delivering that current. Even if you don't include voltage sag into that. So if you're in that top, where you're really hammering that battery to the wall and you're having significant problems with voltage sag on lower voltages, then you absolutely will get more flight time out of a 6-cell pack, even if it's equivalent milliamp hours, or milliwatt hours, even if it's equivalent milliwatt hours. But if it's equivalent, if you're just cruising, and say you're cruising at like 45 miles an hour, fairly low current, you're going to lose flight time going to 6S if you take equivalent watt-hour packs. Now, the reason why most people think they're gaining by going to 6S is that they're honestly most of the time using larger capacity packs. They're using 1250 milliamp hours 6S, and they're using 1500 milliamp hour 4S. But that's like a third more wattage in the 6S pack than there is in the 4S pack.
And that kind of leads to my next question that we brought up before we went live. I do a lot of troubleshooting, and mostly like I deal with micros a lot. I do the micro quad squad, all that. But I've gotten a lot of people that fly 5-inch asking what they need to change, what settings they need to do to make the jump from 4S to 6S. And that's interesting with all that, because I was assuming that they would need that it actually was more efficient, but it's not. And is that where the throttle cap comes in to help with efficiency, or is that just to not burn out the motor?
Yeah, it's mostly not, and it's mostly to control that top end of current, because obviously, again, if you're keeping KV constant, the higher the RPMs go, there's a nonlinear relationship between RPMs and current. Okay. So as the RPMs increase, the more they increase, current keeps increasing at an exponential rate to RPMs. So if you're keeping the kV the same and just adding voltage, you're very, very quickly going to get to the point where the current gets out of control. So basically that there's two reasons why you might put a throttle cap on. One is to make the quad easier to control. So you're gaining some of the advantages of the higher voltage without sacrificing your control at the top end, or you're gaining back some of that throttle resolution that you might have, where at an unlimited 6S voltage, you touch the throttle and it's just gone. So if you put that cap on there, you're gaining throttle resolution.
Without it, it's kind of like going from flying a Cinewhoop to flying a 6-inch race.
Right.
So here's my question on throttle cap, and I had this discussion with a couple of guys at the field. My theory is if you're using a 80% or a 90% throttle cap versus 100%, if you no throttle cap, you're flying all out and you're turning. You have no way to go plus for the motors driving the outside. You have to slow down the motors on the inside only. Whereas if you're at 90% or 80% throttle cap, you're actually giving the flight controller a little bit of room to actually increase the speed of one as it decreases the speed of the other, and then should give you hopefully a little quicker turn for racers.
And more authority on the PID controller too. I mean, that's definitely a critical part of that. The other piece to that is that it might be an interesting experiment to combine throttle cap and motor output limit. Because the throttle cap by itself, if you're using the throttle cap feature, it doesn't cap the actual output of the motors. It's the motor output
radio,
limit. Right. Well, it caps the input, but
it caps what it accepts as an input.
Right. So you can adjust that. Well, it maps it, is what it does. It takes your throttle range, 0 to 100 of input, and maps it to like 0 to whatever your
1850 or whatever, right?
Right. So whatever that it maps it down. If you're used to programming it all, the map function makes sense to you. But if not, go look at it. So combining the two might get you an interesting result as far as you can limit the output, the max output through the motor output limit, which would, absolutely limit that top current and help prevent you from smoke and stuff. Yeah. And then you can also play with combining that with reducing the throttle limit that gains back some of that throttle resolution, but leaves some of that overhead in place for the PID controller to use.
Right.
Yeah. So that's
so I kind of had the right idea. So, and it seems to me that the usage for racers is just to keep them out of that max throttle, but for freestyle, it's more I see a lot of people using 2400 kV motors, 2500 kV motors, even on 6S. Mm-hmm. And you really want to cap that throttle so you don't smoke your ESCs, smoke your motors, stuff like that. Yeah. So I guess it kind of depends on your application, right? Whether you're going to use it, how much you're going to use. I'm more interested as far as ESC tuning. How come motor manufacturers aren't giving us the ideal timing and the ideal motor braking setup for these motors? I mean, they're doing all these testing. They're manufacturing, right? Their engineers should be able to tell us something like that for the size of the motor, what timing we should be running to get the most efficiency.
Sure. Yeah. Well, the thing that I've found in a lot of this is that a lot of the manufacturer engineers don't know. Yeah, they don't know.
Well, I mean,
a lot of times what they're doing is just
be able to calculate the most efficient timing for any RPM for that motor, and it should be very similar based on the size of the stator, right? Or I was saying before, the actual individual pole winding.
Well, but again, depending what's ideal might depend on your application. A lot of times that's the case. So. But the real thing is, like, a lot of these manufacturers, they're just duplicating designs. Like, they're just taking an off-the-shelf stator, they're putting a new fancy machined bell on it that looks different. They're slapping in whatever magnets that they can get and producing it and putting it out the door. I mean, as far as the actual engineering that goes into these things, there's almost none. Like, they literally don't do any of that. They may do some testing just to detect the current. And, they check to make sure that the temperatures are within the rated range of the magnets and windings that they're using. Yeah. But, that's the extent of the engineering that they're doing. They're not doing extensive magnetic modeling. Some of them, now, don't get me wrong, some of them are. Some of them are doing more magnetic modeling and actually testing, to see what the stators are and what thickness of the flux ring they need to use to get the optimal magnetic performance on the bell. Some of them are doing that, but a lot of them are just replicating designs and pushing them out the door.
Right.
So
timing would probably vary a little bit with your PIDs too, as well, right?
No, but it might vary more with other ESC settings and other. It depends really on what you're trying to accomplish. So going to higher timing is going to gain you a little bit of resistance to desync. It's going to give you a little bit more power, tiny bit more torque, but it's going to cost a little bit more in terms of efficiency and current. And heat, right? So, and what we're seeing now is that a lot of these BL32 ESCs, the FedTech stuff, a lot of these more advanced ESCs are doing auto timing, so they're actually detecting that and adjusting the timing on the fly based on the bent feedback. So I usually turn that off because that's going to give you the most efficient, running of the motor, but it's not necessarily going to give you the most effective running of the motor.
Yeah.
Okay.
So I'll usually turn that off and just push the timing up higher because I'm more interested in desync resilience. I'm more interested in power and in response time. So those are I almost always push it up to 23 to 25 degrees on pretty much across the board.
Yeah.
Because you're going to have less likelihood of a desync and you're going to have better overall robustness of the performance just by pushing it up. And if there are other things that you can do to kind of pull that back in to make it a little bit more resilient. Because, there's always, as you go up in the timing advance, you're dumping more current. You're firing that ahead further so that there's more time that the coils are turned on effectively.
Yeah.
So there's more risk of it, if it's blocked or something like that, of it dumping current into the coils. But at the same time, there's other things that you can do in the ESC settings to back that off, like reducing ramp up power, and doing some other things that might be more effective at limiting that current, but without having a performance cost that the lowering the timing might give you.
Awesome. Well, with that being said, let's talk a little bit about ESC protocols in general, because we've talked a little bit about the BL Heli 32. In terms of with the new Betaflight and all the filtering and stuff, there's some ESCs that will not work for it and that will make your motors super hot if you put filtering on or anything without setting the ESC up with bidirectional.
Right.
And I, being the head of micro quad squad, a lot of mine are micros, which means BL Heli S, unfortunately. But I've found a lot of success with JESC. Now, in terms of the normal BL Heli protocol and the JESC / Jazz Maverick or whatever, I haven't even tried Jazz Maverick yet, so I don't know anything about it. But in terms of those, what are the main real differences that are giving it the capability for bidirectional and the D-shot filtering and all that?
Right. So standard D-shot is just a one-way signal. It sends a series of pulses that represent bits, like on-off.
The packets. Yeah.
Right. So it has to do with the length of time the pin is high versus the length of time the pin is low. So it represents either a 1 or a 0, creates a digital signal and pushes it down. The SC decodes that, sets the throttle value, and it's done. So what bidirectional has done is it's every time a packet gets sent to the ESC sends a packet back that embeds an encoded RPM value, essentially. So it's getting a throttle value, it's spitting back an RPM value. So one in, one out. So it effectively halves the speed of whatever D-shot protocol you're doing.
Yeah.
So if you're using D-shot 600 bidirectional, it's effectively sending at D-shot 300 and receiving at D-shot 300.
Yeah. And that's why, this was a tricky one. I had a lot of people saying, oh, but I'm running D-shot 1200. And I'm like, but that's not necessarily faster packet transfer. That has to send smaller packets to be able to keep up with that. Am I correct?
Well, no, it just has to do with the protocol timing, like how long the pin is off versus how long it's on. So it's sending the same amount of data. It's just sending it more quickly, because it's taken that time scale and shrunk it. Yeah. But again, D-shot 1200 bidirectional is equivalent to D-shot 600 monodirectional in terms of how often it's sending. So it's basically sending D-Shot 600 down and receiving D-Shot 600 up. But because it's twice the traffic, it's still running that lower time spacing on the protocol itself.
Okay.
Right. Now, where we're setting the frequency, we're actually setting how often it's sending the packets, correct?
No, so this is something that's completely different. So your D-Shot protocol has to do with the communication between the flight controller and the ESC.
Yeah.
Okay.
So D-Shot 600, D-Shot whatever, or multi-shot, or basically that's the communication.
One shot 125. Anybody using that anymore?
So, and then that's tied to the PID loop in the flight controller. So how often it's sending an update has to do with how often that PID controller is making that loop. So, 8 kilohertz in beta flight, maybe faster in flight 1. So that all has to do with how that's being transferred down the wire to the ESC, and in case of bidirectional D-Shot, back the other way. Yeah. So the PWM setting in the ESC has nothing to do with the flight controller at all. Just completely upstream, completely different. So what PWM is dealing with is downstream. So it's between the microcontroller on the ESC and the FET itself.
Oh, okay.
So it has to do with how often it's the frequency of the duty cycle between the MCU and the FET. So that it could also be between the driver and the FET, but it depends on. Some of the ESCs have the driver built into the MCU. And back in the old days, we didn't use drivers at all, and it was just direct drive to the FETs. But the point is, it's between whatever is controlling the FET and the FET. So the duty cycle, you have, when you're talking about duty cycle, you have two components. You have, or when you're talking about PWM, you have two components. You have frequency and duty cycle. So frequency has to do with what the maximum length of the PWM can be.
Yeah.
And duty cycle has to do with how much time out of that maximum length is being actually driven on versus off. So if you have a 50% duty cycle, that means for the amount of time of the frequency, it's on half the time and then off half the time. If you have a 20% duty cycle, then it's on 20% of the time and it's off 60% of the time. And vice versa, if you have a 60% duty cycle, it's on 60% of the time and it's off 40% of the time. So, you've got, but the frequency has to do with the maximum length of time between those two.
Okay.
So the frequency has, and again, changing the frequency changes some things about how the ESC operates. You have some things like dead time that have to do with how long the ESC has to wait before it turns the high phase off, the high side off and the low side on, or the low side off and the high side on. So there's a little bit of a delay between those two to make sure that it doesn't create a short circuit between the two sides of the FETs. So that PWM frequency changes the relationship between dead time and the total cycle commutation time. So all of that plays a role, and this is part of why I want to do this testing on 24 versus 48 kilohertz, because we don't really necessarily know from a quantitative standpoint exactly how that's changing the performance of the ESC. We have a lot of theory. People are saying, if you go to 48, it reduces torque. But some early testing that I did didn't seem like it was reducing a whole lot of torque. And it depends on where in the throttle. Because, again, at lower duty cycle, you're seeing different behavior than you are at 100% duty cycle. Because it has to do with how long it's on versus how long it's off. So there's a lot of variables in that. But the rule of thumb that I follow when it comes to PWM rate when I'm tuning my ESC settings. So red flag, this is the important bit. Ignore all the drivel I was saying before. If you didn't understand it, that's fine. This is the important part.
So log in now is what he's saying.
Yeah. So the important part here is that I generally will run higher PWM in one of two situations. So I run 48 kilohertz on very powerful large motors or on tiny motors.
Yeah.
So those seem to be the two extremes where it works. So you have this kind of center area where you've got mid-power 5-inch kind of standard motors that may do better at 24 kilohertz. But here's the thing. 48 kilohertz, because of the way it interacts with the ESC, has a much lower noise floor in terms of back-driven noise.
Yeah.
And you may also run into issues, especially at low throttle, where you're getting grinding or hot motors. because of the 24 kilohertz, because of the way it interacts. Where if you're getting that, going to 48 kilohertz will almost always solve your problem. It's gonna reduce the noise. It creates a lot less electrical noise through the rest of the system. Video noise might go away. But again, there is no solid, like this always works all the time.
Yeah.
My rule of thumb is to try that first, and then if I have issues, then I'll back away. What you'll see if you're running 48 kilohertz on a rig that shouldn't be running it, you'll get low throttle wobbles. You'll get kind of this, you're flying forward and it just kind of, it wants to meander a little bit and bounce around a little bit. So that kind of just instability at low throttle tends to be a sign of that you might need to drop to 24 kilohertz. That being said, you can usually tune that out by raising your P gains significantly and using more TPA. So like if you jack your P gains up to the point where you're probably almost getting oscillations at high throttle and then increase TPA to pull those high throttle oscillations back, those low throttle, mid throttle wobbles will probably disappear. So you have to kind of play it by ear. This is why, again, usually I almost always try 48 kilohertz first and see if I have issues, because that's the safer bet. 24 kilohertz, you can get those hot motors, you can get grinding at low throttle. You can just in general get some of that nastiness that can be harder on your gear. So I'll typically go 48 kilohertz first and then back down to 24 kilohertz just to make sure.
Yeah, and
sorry, Dan. Go ahead.
I was talking to you, Ryan, today or yesterday about the build that I was working on. It's a 6-inch frame with 5-inch parts, pretty much, just for the stability. And you had me go to JESC 24, which seems to be working great, by the way. I flew it. Unfortunately, the VTX is having issues, so I got to swap that out. But I did some test flips and line of sight, and it flies great. On all the micros that you've helped me set up JESC with, I've done 48, and they are working just fine as well. But they're all below 12 series motors, you know? So and my problem with the micros, especially with the recent BL Heli, not so much with EMU, but mostly with the recent Betaflight 4.2 settings, micros and their motors tend to just get super hot with the stock settings. And I really found that the 48 helps with the smaller motors a lot, but also I haven't had time to test the 24 kilohertz setting either.
Well, on micros, again, that's where you pretty much where 48 kilohertz was originating, and even some of the really small ones, 96 kilohertz is even better. The RPMs are so high; they're often. I mean, if you look at some of these micros, somebody sent me a picture of one that they were working on, and they literally took like a 1204 motor, and took half the magnets out of it. So
I was sending you
that's it. Yes.
It's got 6 magnets in it, but it's supposed to have 12, and those magnets
so they took
are
half
held
the
in
magnets out.
Yeah.
And you can see that there was space there for the others. It's probably exactly the same bell that they use on their half.
Where's the rotor for that one?
It's still a what was it, 9 that we?
Still a 9-pole.
Yeah, a little 9.
So what they did literally is they had a 7,000 kV motor, and they were like, "We need a 14,000 kV motor."
It's 15,000, I think.
Yeah, right. So they have probably a 7,500 kV motor, and they were like, "Well, we don't have to change anything. All we have to do is put half the magnets in, and voila, 15,000 kV motor."
And
so,
I've got, this is an 1103, and usually things over 10,000 don't come in that big of a size.
Well, and there's a reason for that, because you only have so much space. I mean, you have to have a certain amount of copper around the winding, and by going up in kV, you're reducing the number of turns. So you get to a point where there isn't an effective amount of copper around the windings to get the proper number, to get the proper torque production. So probably the only way they could make a motor that high kV was to reduce the magnets like that. Now, I think ideally they probably should have reduced the number of magnets and made them wider magnets, but that would have required machining a new bell, and this was way cheaper. So
I've got it on a 2.5 or 2.3 inch or whatever frame, and I've got a bunch of these motors on it. They seem to go well, but when I set it all up bidirectional, and it gave me the option to choose poles. It was automatically at 14, as most of them are, I think. But after talking to you when I showed you those, I tried it on 12, and they spun fine. They weren't doing the jittery thing that they were doing before. So I think that's very much the
But
case.
the RPM calculations would be off. That's why you have to put in the number of poles. So the RPM filter would be off by a factor of 2 from that, because you've got, or double. I don't know, that's not a factor of 2, but off. It would be calculating half the RPMs of the actual RPMs.
It wouldn't let me put 6 poles in.
Right, which is probably because they didn't realize that companies were doing 6 poles. But
A-OK fly.
Yeah.
That's all I can say.
I mean, I've flown some of their motors in the past, and they were pretty smooth and decent. But yeah, that's definitely we need a higher kV motor. Let's just remove half the magnets. It actually brings an interesting discussion about that relationship between kV and magnetic field strength. Because there's a direct correlation. The higher the magnetic field strength of the bell, the lower the effective kV with the same number of turns.
Yeah.
So if you took, if you had 2 bells, you had exactly the same stator, right? Same number of turns, same stator. You had one bell with, N45 magnets and one bell with N50 magnets. The N50 bell on that motor would produce probably 200 kV lower than the N48 bell.
Okay.
Just because of the difference in magnetic field strength. So you can actually tell something about the torque production capacity of the motor in terms of air gap, magnet strength, all of those factors, the flux ring design, all of that. So you can tell the quantitative production of torque out of that bell if you check the number of turns that it's taking to produce a given kV. So if you compare it to another motor that's the same effective kV, and this one has, 9 turns, and that one has 10.5 turns, then the one with 9 turns is a higher torque motor than the one with 10.5 turns.
Okay.
Assuming all other variables are equal, that's going to be true.
I have a lot of really big motors.
For a smaller motor to reduce the number of poles and magnets, regardless, you could actually fit more windings per pole.
Right. Yep. And that's why they did it, because if they tried to do that with a 12-pole bell, they would have like half a turn on each stator to get that kV, and then it wouldn't work. It wouldn't work.
Yeah, I want to figure out how to properly set these ones up so that the timing's okay, because I want this thing to fly, but they all, it's kind of also just novel, because I'm looking at it going, you don't see motors like this. You don't, you never find them. They're always crammed in there.
Did you try going to CLI and actually typing in 6 from the CLI?
No, I did not, but I will.
Because if you do set motor poles equals 6 on CLI, I wonder if it will take it. It might just be that the GUI doesn't let you set it that.
Okay, because I still have, because I blew one motor first testing it, and then I had to order more and replace them. I haven't soldered the new motor on, but the first motor, when I blew it, it was just set at 12, and it was giving me the jitter when it started trying to hover.
That's probably not. Well, I guess if you're hovering it, if you're driving it from the motors tab and you were getting jitter, that wouldn't be related. But
no, it was literally on the test flight, and it hovered up just fine, and it hovered, and then it just started each motor was doing this, and it was still hovering, but it was going everywhere, and so I just disarmed it. Yeah,
the filtering would have been off by half.
Oh yeah, and I brought it down, and when I went to try, I was like, okay, what's happened? I went to try plugging it in again, and then one motor just wasn't going, and that little puff of smoke, I was like,
out.
fuck, all right.
All right, so
go ahead, Matt.
Brock had a question related to the 6S stuff we were talking about, 4S, 6S. He's asking what's the best way to pick a 6S KV for different weights of quads.
Right. So generally speaking, the lighter your quad, the higher the KV. This is true regardless of voltage. The lighter the quad, the higher the KV you're going to be able to get away with without problems, because the way the load is represented on the quad, it's going to unload more in flight. You're going to get more forward motion for the same number of turns because there's less weight holding it back. So generally speaking, the heavier the quad, the lower the KV, the higher the quad, or the lighter the quad, the higher the KV you're going to be able to get away with. Now, obviously, some of that depends on what you're wanting to do with efficiency. So if you're looking for like the most efficient setup, you want to go both light and low kV.
Yeah.
If you're wanting and low voltage, actually, like the most efficient setups that I've seen are like 3S, 1700 kV, like just barely enough to lift the quad. That's going to be your most efficient setup. And there's a reason for that, because there's an efficiency curve for brushless motors. They kind of start out fairly low efficiency, and then they increase in efficiency up to about 80% throttle. Yeah. And then after 80% throttle, they start dipping down again. So the closer to that 80% throttle range you can actually get your effective flying, your effective use of the motor, the more efficient that motor is going to spin. So combining your voltage with your kV in a way that it's sitting at the point on that curve where you want it to sit for the efficiency that you're looking for is going to be the kind of the go-to for that.
That's going to be a vital step too, because I see a lot of people coming in to the hobby not knowing much about kV or which motors to put on what things, and you get people that build up a really heavy Martian frame or something with just like they're like 2850 or whatever. And you're like, what are you doing? Like,
I mean, that can fly okay if you know how to handle it. But
my iFlight, it was pretty heavy. I had the XL5 set up for a little while, and I was running 2750s on it on 4S, no problem. It had no problem. But I tried that same setup on just a no-name like Flyno Skull knockoff sort of frame that was just super heavy, and it was a completely different experience.
Yeah.
This right here was probably my favorite setup, and it's got 2208 2000 kV, and I run it on 4S, and if I really want to go nuts, I put 5S on it, and it's freaking just perfect.
And that's an interesting thing, because I honestly feel like 5S is probably the sweet spot for 90% of what we want to do, and I've always been surprised that more people haven't done it. I think a lot of it has to do with just the fact that there aren't a lot of 5S batteries out there. But you talk about like the difference in efficiency between 4S and 6S, but 5S kind of hits that middle ground where you're getting the power, more power than 4S, better voltage sag handling, but also you're not getting, you're getting better mass efficiency at 5S than 6S.
Yeah.
And so like there's this kind of sweet spot there at 5S that I feel like definitely should be more further explored. But, it just doesn't seem to have ever caught on.
Our FPV community seems to be filled with a lot of the go big or go home types.
That's true.
That's where 6S came from.
Well, so I live in Austin, Texas, right? So, and do you guys know Gil Coronado?
Here's the name.
He was a DRL racer a couple years back.
Yeah.
Super fast, freaking crazy fast guy. He's been kind of getting out of it a little bit lately, but I've been working on him with working on some side projects with him and stuff. And we talked about that a lot, about 5S being the sweet spot. Yeah. And it's just, there's not a lot of motor, especially for racing. He still runs 5S for racing, but I think he's using like 2300 kV motors. Mm-hmm. So, but he swears up and down that's the sweet spot. And he refuses to change. There are quite a few 5S.
Well, and there's something else to be talked about especially for racing, when we talk about 6S versus 5S versus 4S, because, we talk about Ohm's law, but really I think we're talking about a derivative of Ohm's law, because Ohm's law is actually V equals IR. It has to do with resistance. We're not doing resistance, we're doing inductance in brushless motors. But what people are really talking about is the watt equation, right? So, watts equals volts times amps. So if you go up in volts, you go down in amps to produce the same amount of watts. But here's the thing. In brushless motors, torque is proportional to current, not power. So, and again, we talked about RPMs being nonlinear, but the point is that at low RPMs, a 6S setup is going to be drawing less current for the equivalent RPMs than a 4S or a 5S. And given that current is proportional to torque, that means the torque available at low RPMs is going to actually be lower at 6S than 4S or 5S. Now again, since current is not proportional to RPMs, it's exponential. As you go higher in the throttle, that difference mostly goes away, and it's really only at the low end of the throttle that you feel it. But if you talk to anyone who has raced 4S and 6S back to back, they're going to tell you that 6S feels a little bit mushy at the very low end. Like if you're flying around in the low part of the throttle, you're going to get just a little bit of a mushier feel. You're going to hover at a higher throttle point with 6S than you think you should going from 6S to 4S. Or 4S to 6S. Like, it just feels like I just went up in power, but I'm still hovering at like 20% instead of 30% throttle. It feels like I should be hovering at like 10% throttle. But the reason why you're not getting that is because that relationship between torque and current, not torque and power.
Yeah.
Okay.
So I noticed that actually with going from 3S to 4S on the Gank Racer Mini. It's all good. On Matt's little 3-inch, which is right here. Hold on.
It's a tiny 3. It's a micro 3-inch.
Yeah.
Nice.
It's literally like a racer body, very super light, and it's great. I've got 14 series motors, and I've literally jammed a 20 by 20 35 amp stack in it.
Yeah,
so I
didn't leave a whole lot of space for the 20
no,
by 20.
like if you want to see, there's literally a millimeter or two between the camera and the stack there.
If he ran my cam angles, it wouldn't fit.
Oh yeah. But this one, I jumped from 3S to 4S, and it went to start hovering at like 10%. It was awesome. But then it had the constant extra speed, but I noticed the battery wore out real quick.
Yeah, because you're hitting that higher RPMs.
Yeah. So
I can get about 4.5 minutes on this with a 3S 650. It's got 1106.
Yeah.
I think it's like 4,000 kV maybe, or no, 6,000.
I'm running the 3S 550 milliamp, the GNB batteries, and I was running the 4S 450 milliamp on this as well. But I was getting around 4 minutes of flight.
Yeah, and with the 4S, you were carrying, a third more watt hours. Yeah, so you were really suffering on the efficiency front.
Oh no, the 4S is one of the super tiny ones though. So the weight, it was the same weight as the 3S would be.
Right.
But
you're still carrying more watt hours because it was higher.
Yeah. Oh yeah, exactly. And but the 3S, I really liked how it flew. Like it just was smooth. The rolls and flips were there. Everything was tuned in and locked. The 4S just seemed like insanity to me when I was flying. It was like I couldn't control it as well.
You're probably a little high in the KV though, aren't you?
I've got, what do I got on here? 3,600. That's not too bad.
No, you're good.
Yeah.
My Cinewoop is the one with the 4,000 kV.
I've got a toothpick that's got 4,100 kV, 1404s on it,
nice.
And that thing is like the most efficient thing I've ever flown. I've been flying 4S 450s on it, and it gets like 8 minutes of flight time. It's ridiculous.
I have a 3-inch with actually 11 series motors on it. There's 11, the old Flight Test Gremlin 1104s.
Nice.
I think they're 5250 kV or something like that. I'm actually running that on 3S, which they really shouldn't be able to handle in the first place. But it's a pusher plus sort of setup. So the 3S 550 milliamp battery lasts a good 3.5 to 4 minutes on that thing too, and the motors aren't even hot.
Yeah.
And it has to. I know it has to do with the layout of it and that it's a pusher and all that. But I honestly didn't even think those little 11 series motors would be able to handle that. Let alone
honestly, the biggest factor in efficiency, from what I have found, is weight. Like, that's really what it boils down to. Like, if you can reduce the weight, you're going to dramatically increase your efficiency, period. It doesn't matter what you're running. Like,
this thing's
weight
lighter
is the
than
biggest killer.
Yeah, this thing's super light. It's and so here is it flying forward.
Yeah.
So it's the weirdest little thing ever, but it's great. I love flying this thing.
I really do like Plus designs. I've got two Plus designs that are pocketed just because they never really sell very well, so I'm not that anxious to produce them or even put them out. But honestly, I've probably got 12 quad designs that aren't quite complete that I could put up pretty quick.
Yeah.
Yeah.
So I'm popping into your web page here, and I gotta say, anybody who's looking for stats on their specific motors, definitely check out Ryan's page Ryan's website. It's miniquadtestbench.com. And here we go. So go to the Data Explorer.
Yeah, that's where all the new stuff is.
Yeah.
And honestly, like, we've slowed down a bit on testing just because there hasn't been much new stuff being produced. Like, most of the motors that are out now are just duplicates. You know, you're seeing a lot of stuff that's just the same stuff with different bells slapped on it. You know, so that's
exactly
the motivation that's why I'm trying to focus more on testing some of this stuff, like, you know, the differences between wide and tall stators and some of this other stuff that's more could help push us forward into like better development instead of just testing the same thing over and over and over again.
Yeah. Now, Ryan, in scanning your site, I gotta ask, do you still have any of the Crush Light, the 3-inch?
The frame.
Because I might have to buy one.
Well, I have a CNC in my garage. I can cut you one if you want. But yeah, I think they sold out, and I haven't really. I'm doing more contract work now than my own designs. So I do a lot of designs for other companies, but I haven't really been producing any more of my own. So
that was a cool little rig.
Yeah, it was great. It flew good. I actually even made a version with prop guards on it that you could bolt to the bottom. Had like pockets machined out to where it would bolt onto the bottom of the arms and everything. I have one in the garage. It worked really well, but yeah, there's so little return on frames. I was literally losing money to produce them in the end. So
Matt's one that you can talk to about that. He spends a lot of time designing frames.
Yeah, like I said, I'm not. Fortunately, I have a well-paying, secure job, and this is just kind of supports my FPV habit. I'm not looking to make a whole bunch of money, so you're probably not going to see a $70, $80, $90 frame on my page. But
Yeah.
Well,
I'm not going to make a whole lot. I'm not going to make a whole lot on them. But like I said, people have been asking me. A lot of my friends have been asking me to start producing some of the ones because I just started designing for myself. Right? I didn't
exactly. That's what I did too.
Like certain frames and.
Yep.
Like I designed my own freestyle frame, the Nemesis. Where'd it go?
But it's I love designing. I mean, that's really like I said. Like Matt said, it's about, you know, I saw things that I didn't like. I wanted to try something different, put something together, and somebody was like, "Hey, you should produce those." And Heli Nation picked up the first batch of the Crush, and from there, I just kind of got into designing for other companies.
So this one here, I had the design. I kind of. Made myself, right? It's got a little bit of a recessed GoPro. It really helps hold the GoPro in there, but you've still got access to charge and get your SD card out without removing it from the cage. Did some 5mm arms, isolated the flight controller from the arms, so there's larger holes where the flight controllers mount through, so there's no vibration when the arms passing through the frame. I went super slammed on the back with 18 mils in the back, 25 mils in the front. And then I've got a 30 by 30 VTX in the back. There's 30 by 30 mounts, but this one here, I just there was nothing else out there like it. So I was kind of looking for something really smooth, and I wanted a 6-inch. Most of the other 5-inch frames weren't designed as a 5. This only comes in a 6-inch. Well, it used to come in a 6-inch. Sorry, I don't make.
Not available anymore. Yeah,
I don't make those ones anymore. So technically, that's probably one of the last few in existence. I think Matty Blunt's has got one. I think a couple other people probably have one out there, but I keep getting asked to bring it back. But like I said, I started designing for myself, and it just kind of.
You should just open source the design there.
Yeah, I like the racers. I didn't like how the racer was set up. Most racers are really, really tiny, right? So not a lot of space to build. So it made it really difficult. So this is the first racer that I made. It's a little bit longer. It's got carbon fiber cam mounts in the front. Plenty of room to build, and you don't have to kink your antenna wires around or anything. And it's durable as hell. It's got easy swap arms, but it just kind of no flex. And then I did the Mutiny freestyle frame, because I wanted something, I wanted a freestyle frame that was light. A lot of the freaking freestyle frame, like I made the Nemesis, and people were complaining because it was 130 grams dry, 120 something grams dry, and I was like, dude, it's a 6-inch. It's meant for smooth video. It's got the low GoPro, so you can get really close to the ground. I said it's kind of a purpose-built quad, right? It's not a one-size-fits-all freestyle thing. This one here, I wanted to make it light, so I think these ones come in at like 90 something grams.
Nice.
But they've got a unique bottom plate design, and then easy swap arms. I just kind of, that one's a 6-inch, and then I built this 5-inch version, so I can do toilet tank or standard mount on the top as well. I just like to give people options.
Right.
Yeah,
my goals when I approach designs are usually like I try to make them as simple as possible to still accomplish the design goals. Like I try to take my concepts and boil them down to as few components and as few pieces as possible. Like just conceptual pieces. Like I want to boil it down until it's as simple as I can get it. So
right,
that's,
like the racer, when I built that, I mean, everybody was still using dual bottom plates, right? And having the arms interlock in the middle. And I kind of went to this, I've got just a really small, probably, 1/2-inch by 2-inch arm plate that bolts on top. And they've got, I don't know if you can see them or not, but I've got press nuts in there. So it's really just remove one screw, loosen one screw, the arm swaps out. You don't need a lot of surface area to clamp onto that frame. But it brought this one, like this one's built with 20 by 20 pyro stack and 2306 motors, and it's like 280 grams or something like that. So it's not crazy heavy, but it's not, it's not super light either, but it's still competitive because 70 gram dry weight. So it's where the floss light was before they became the ultra light, when they made it 20 by 20 only. Yeah. So I mean that was kind of my goal, is to get it somewhere out in the price point of Pyro's putting their frames out, and somewhere around the weight that they're putting their frames out, and give people something that's not a boring freaking cube to look at. I'm so sick of looking at square top plates, square bottom plates. It's just kind of, the imagination's gone. You know what I'm saying? Yeah. So I kind of gave mine a little bit of shape. You know what I mean? But I don't know. Like I said, I just started racing it myself, and then I started racing. I'm racing in Austin and Dallas and Houston, and I get a couple people see my frames, and hey, man, that's pretty cool. What is that? It's mine. It's kind of. I like being able to say that, but it really is kind of.
It's cool seeing your frames out there. Like I think I have. Last I counted, I think I have about 12 or 13 on the market right now from various manufacturers, and it's cool to see people out there flying stuff. And
it was the weirdest thing for me last year. I went to Multi GPIO, and I've been for this would have been my 3rd year, but they, of course, COVID. But so I went out there, and I was having people come up to me like I didn't know. Oh, dude, I know. Yeah, you can. Oh, dude, let me see your frames. And they're like, I've been seeing everything in the pictures and. All this stuff, so it was really kind of odd because I'm not that kind of person. Right. It makes me feel awkward, and it doesn't really kind of boost my ego. Or
anything. I hate putting myself out there. Like none of the frames that I designed, except for the Crush Light and one other that I did for a friend of mine, have my name on them at all. Like I'm just not interested in even with Mini Quad Test Bench. I don't put my name out there. I hate that. I hate the the hype and all of that jazz. I'd rather just be who I am and help people from behind the scenes.
I have to use my name because Gank Multi-Rotors is just such an awesome freaking.
Well, yeah, exactly. Gank. I mean,
it's like my friend's like, dude, if you don't use that, he goes, man, you were gifted with like the name
exactly.
for a company for quads, right?
Yeah.
So, and there's already there's a couple people that already start hashtags Gank Tough and Get Ganked and stuff like that. I'm just laughing about it, but. My buddy Chris Bolter, he came up with my logo for me, and dude, I freaking love it. Yeah. Like you can't. I told him, I says, he showed it to me. He goes, "What do you think?" And I was like, perfect, dude. Because you got the little, it's got the little swoop with the G, right, for the logo for the name, and it's kind of like I like the font that he pulled out on it and everything, and it's really nice that I can get the logo and the name cut out into the top of my frames if I need to.
Nice.
So,
looks like we lost.
Yeah, we lost Dan. He sent me a message saying his internet just crashed.
Yeah.
So that's kind of a bummer.
Bummer.
But so anybody in the audience? He said he's restarting. He'll be here in a sec. Anybody in the audience have any questions for Ryan related to quads, tuning, anything like that?
On my phone, so I can actually read people's comments.
Yeah, I don't have the option to post them and stuff like that. My dog's going crazy right now. It's not playtime. I'm sorry. We'll play later. Okay? We'll play later. That's Nix. She makes frequent appearances when whenever I'm on a live stream for more than an hour. She starts.
We just got a new kitten. My wife decided it was time for another one. So that's good. My boys are.
Nix is only 7 months. She's actually 7 months old in 2 days, but so she's still got a bit to grow.
Yeah.
But she's a freaking monster. So yeah, this yanks for you, Jeremy. But yeah, I think the hardest thing for me is coming out for names for the frames. Yeah. There's nothing ever like me and Nemesis. Those ones, as soon as I was kind of spouting them off with a couple of my buddies in a private chat, and those ones just kind of as soon as I said them, I was like, yeah, that's perfect. But
that's the nice part about doing contract work.
You don't have to worry about that, right? Yeah,
they just tell me what they want, and I'm like, okay, here you go.
Yeah, I got approached by a company in China to ask me if I would be willing to design a frame for them to distribute from China, and I was like, let me get my stuff settled and get because I just got the website up last week, so I'm still kind of making tweaks and stuff as people tell me about bugs, or if they say, hey, the description's weird on this one, or just trying to fix that